Good evening, everyone. So myself, Nivin, so I'm from Panic E-Learning. So today, this is the second day of the AI robotics session. So we'll continue where we left from yesterday. So uh, yesterday, ma'am actually gave a good idea about artificial intelligence and robotics, and she talked about specifically about medical robots. So I'm not going to focus on that particular area. We will be talking about AI robotics in general, and then we will have our own specific. We will see how our own, how to make robotic applications using our own specific tools and programs that we use in. So so the whole session is going to be, so today we are going to talk about all these two things like artificial intelligence and robotics. And then we will see a hardware, hardware that is actually we can use in AI robotics. And then we'll see how to configure that and specifications of all the hardware and how that can be used. The hardware can be used in any type of AI-based robots. So before going into artificial intelligence and robotics, first we have to see what is artificial intelligence and what is robotics. So at its simplest form, so this is just a definition of what is artificial intelligence. So at its simplest form, artificial intelligence is a field which combines computer science and robust data sets to enable problem solving. So this is more of a definition from point of view of today's world, like whatever machine learning, deep learning, all these developments are happening, and this simple definition, this one line that we have read just right now, is just from that point of view. But artificial intelligence can be anything, like even a simple video camera can be seen as a weak artificial intelligence. So it is doing a specific task like recording, capturing the images and saving the images in a disk or a memory, or whether it is a cassette, whatever it is saving. So it is doing that task again and again. So it is something that humans are able to do. Like it is a part of our intelligence, the vision, and how we can record like each scenes, whatever we have seen. So all those things are whatever we have seen. Everything is recorded, and like significant things are stored in our brain, in our memory. So the same thing can be implemented with in its simplest form using a simple video camera. So that is as simple kind of weak artificial intelligence. So, but when we say artificial intelligence from today's perspective, it involves machine learning, deep learning, data science, all these different technologies are involved when we're talking about artificial intelligence. So here the first line, that's why the first line is written like that, which combines computer science and robust data sets to enable problem solving. So it is used for problem solving, and it also encompasses subfields of machine learning and deep learning, which are frequently mentioned in conjunction with artificial intelligence. So artificial intelligence is that if we can say like from a computing perspective, we can say artificial intelligence comprises of machine learning and deep learning. So they both comes under the same umbrella called artificial intelligence. And these disciplines are comprised of AI algorithms which seek to create expert systems which make predictions or classifications based on input data. So that is a general idea here. There is like if you take machine learning or deep learning, any kind of like data science or all these technologies, if you take they have the common characteristics of taking an input, taking not just a single input, taking a set of input, whether it is a linear data or it could be image files, or it could be audio data. We can have so many different types of inputs. So linear data means it could be just so if we take like simple algorithms like linear regression. So that in that the data processed is a linear data. So that we have a single input and the data is the predictions are made based on that single input. So like in case of linear regression, we can use linear regression for linear data, like for example, predicting the salary range of particular set of employees in a so so that is like actually that can be done through linear regression, but the prediction is not going to be accurate because the in case of prediction of employment, like employee salary, there can be, it involves so many different factors. But if you take only a single factor and you're trying to predict based on that single input value, then we can use linear regression in that case. So like in like housing markets, so based on the current housing market value, we should be able to predict next year's variations and fluctuations, so that it with a single set of input we can uh, process the data and get the output from that. So that is one type of processing. So when it comes to deep learning, we will be using different type of techniques. So then types of artificial intelligence. So as I explained, artificial intelligence can be divided into two categories: weak AI and strong AI. So weak AI, also called narrow AI, is an artificial narrow intelligence. ANI is a AI trained and focused to perform specific tasks. So weak AI drives most of the AI that surrounds us. Narrow might be more accurate descriptor for this type of AI, and it is anything but weak. It enables some very robust applications such as Apple Siri, Amazon Alexa, IBM Watson, autonomous vehicles, and recently like ChatGPT or from OpenAI. That we can also we cannot call that even ChatGPT the very impressive artificial intelligence chatbot system. Still, we cannot call ChatGPT a strong AI because it's lacking so many different things that a strong AI should be having. So what will so we can see here what is strong AI. Strong AI is made up of artificial general intelligence. So it is artificial general intelligence. So in the case of weak AI, it can only perform a specific. So even if it is able to perform that specific task with very much intelligence and accuracy, still it can only perform that single task. So it is, but when it comes to strong AI, it is called artificial general intelligence. So general intelligence, human intelligence is a example of general intelligence. So we can learn anything and we can apply that practically in our life. So that, for example, if you take any human being, our experience, so our and intelligence, our intelligence itself is totally based on our experience. So it's childhood experience and adulthood experience, whatever experiences that we go through in childhood and adulthood. We learn from that and we fix certain things based on that, and we act based on what we have learned. So that is, we can learn like our brain is malleable like that. We can learn any type of things. So that's why our intelligence is general intelligence. So human intelligence is general intelligence. So a strong AI should be like that. So artificial AI, that is a strong AI. If it is a strong AI, then we can say it is artificial general intelligence and artificial super intelligence or artificial super intelligence. Artificial general intelligence, AGI, or general AI, is a theoretical form of AI where a machine would have an intelligence equal to humans. So you have a self-aware consciousness that has the ability to solve problems, learn, plan the future. Artificial super intelligence, also known as a super intelligence, would surpass the intelligence and ability of human brain. So that humans have general intelligence, but still they have so much limitations. The amount of things that we can learn in a particular time period. We cannot learn like 10 things in one day. That is not possible for most humans, or like other ways. If you are like that level of type of genius, then maybe you can do other ways. Most people cannot do that type of thing. So you can only focus on single thing or two things at a time, and you can learn that. So we have our limitations, but when it comes to a machine, if it has general intelligence like humans, its possibilities are limitless because machines can access so much data at the same time. Its memory is not like our memory. For us, accessing memory is very hard. Like we can access easily, we can access memories that are more registered than memories that are less. Like if you ask me, what did I do like 7 days ago? So exactly, so today is Monday. So what did I do last Monday? I won't be able to remember most of the things that happened that day. Because if it was a significant day, if it something significant happened that day, then I will be able to remember things. So there are like limitations like that with the humans. But when it comes to machines, it is not the case. They can access any type of data or memory, and they process so much data at the same time. And so machines can a general intelligence, a based general intelligence, artificial general intelligence is much more, will become much more intelligent than a human beings. Then super intelligent. So while strong AI is still entirely theoretical, so it is there are no like big examples of like strong AI still entirely theoretical, no practical examples in use today. That doesn't mean AI researchers aren't also exploring its development. So development is happening. So you can see this type of systems in different type of examples in like TV shows and movies. You can find these general AI examples. So like best example is like ASA might be from science fiction such as HAL, the superhuman raw computer assistant in 2001 Space Odyssey. So these are all like general intelligence systems. So we can see like so many like examples where general intelligence can be implemented. So like one example of general intelligence that we can, how we can use general intelligence is like using, so it can take, if we use supercomputers to implement general intelligence, that means it can take terabytes of data at the same time and process that data. So if it is a supercomputer, then that means we can get like you like from all the surveillance cameras from a city to such a general intelligence and ask it to predict any type of crimes. Whenever it is happening, the crime should be predicted instantaneously, and then assistance should be given to the victims. So that can be as like a very good use of general intelligence, and it should be closed system. No one should be able to access that data. Only the AI should be able to access the data, because otherwise there will be so many different type of malpractice could happen in that system if humans are directly involved. So then common machine learning algorithms. So common machine learning algorithms used in neural networks, linear regression, logistic regression, clustering, decision tree, random forest. So in our case, we are going to focus on deep learning. So our subject is artificial intelligence and robotics. So artificial intelligence can be implemented using like multiple algorithms or using a single algorithm. So in our case, we'll be using deep learning, because in deep learning, we can easily we can make use of deep learning too for image recognition and speech recognition, image. So all these things are so deep learning comes under neural network, and so we'll be using that. So you can read from here what are the differences. So neural networks simulate the way of human brain. So it is like a neural network is same as a human brain. So human brain, it fires based on threshold values. So like one neuron to another neuron. So if the decision to activate a single neuron is based on a threshold value, whether the voltage value at the previous neuron is apt to activate the next one. If it is lower than a particular threshold, then the next neuron is not activated. If it is high, then the next neuron is activated, and some pattern will happen, and based on that, some action will take place. So that is how, like, neural network in human brain. So the same idea is applied to artificial neural network, ANN. So in artificial neural networks, there is input layer, and then there could be a hidden layer, and there is output layer. So there should be at least two layers, input layer and output layer. And in most of the deep learning algorithms, there will be a hidden layer or multiple hidden layers. So then there are nodes. So these nodes are like neurons in our brain. So each node is interconnected with all the other nodes. So which pattern should be, which node should be fired, and which node should be activated in a particular layer is based on the threshold value. So it's on the weightage value. So there is weightage value to each node. Based on the weightage, if the weightage reaches a particular level, then that node is activated. So based on that pattern, we'll get a specific output. So it imitates same type of working as our human neural network. So then linear regression, this algorithm is used to predict numerical values based on a linear relationship between different values. For example, technique can be used to predict house pricing in historical data from an area for the area. Then logistic regression, the supervised learning algorithm makes predictions for categorical response variables such as yes or no answers. So it can be used for such a classifying spam, quality control, or a production line. Logistic regression is used for yes or no answers. Like we want to classify, we have a set of data, and we want to classify the set of data as a particular, like whether it is the desired data that we're looking for, or it is something else. So yes or no to classify based on that. Then clustering is used in data science. Unsupervised learning clustering can identify patterns in data. So computers can help data scientists by identifying differences between data items humans have overlooked. And then the decision tree can be used for both predicting numerical values and classifying data into categories. So classification and prediction both can be done using decision tree. And then random forest. In random forest, machine learning algorithms predicts a value for category by combining the results from a number of decision trees. So random forest uses multiple decision trees and combines the results. So then what is deep learning? So in our case, we're going to specifically see deep learning. So we need to see what is deep learning. So deep learning is a subset of machine learning, which is essentially a neural network with three or more layers. So these are so three or more layers. So that in case of deep learning, there will be at least three layers. So input layer, hidden layer, and output layer. These neural networks attempt to simulate behavior of human brain, albeit so still far from machines. Far from matching its ability. So the neural network attempts to simulate the behavior of human brain, but still it is far from matching its ability, allowing it to learn from a large amount of data. So the amount of data is very important, another important factor in case of deep learning or machine learning or artificial intelligence in general. As we increase the amount of data, we'll get more accuracy. So while a neural network with a single layer can still make approximate predictions, additional hidden layers can help to optimize, refine for accuracy. And deep learning drives many artificial intelligence applications and services that improves automation, performing analytics. So deep learning technology lies behind everyday products and services such as the digital assistant, voice-enabled TV. So these days we use it, we see it like if you're simply just browsing through internet and like trying to purchase some product, you will go to different websites. And these days if you take these websites, first of all there will be a chatbot will be available for us for assistance. So we can type any type of queries. Also, if it is the queries are within the range of the chatbot, it will give us the answer. Otherwise, we have to give a specific type of queries. So that is one thing. And then so it uses an NLP for natural language processing and uses NLP and for processing the natural language, the the things that we give it as input. And then other type of techniques like which are like if you take lens card is an example there it uses a type of augmented reality technique to make us give us a virtual trial room. So we can use the virtual trial room and we can try on different, we can turn on our camera and we can try on different glasses and we can see if it is matching or not. So that is one. So depending on the website, depending on the type of websites that we go to, we can see this type of different type of implemented applications. So it all uses somewhere some kind of artificial intelligence and deep learning. So then deep learning and machine learning. So if you compare deep learning and machine learning, so like machine learning algorithms are leverage structured, algorithms leverage structured and labeled data to make predictions, meaning that specific features are defined from input data for the model and organized into tables. So the input data is organized in case of machine learning, labeled and data is labeled and specific features are defined and input data for the model and organized into tables. This doesn't necessarily mean that it doesn't use unstructured data. So there are like two different ways we can use structured or unstructured or supervised or unsupervised learning techniques. It just means that if it does, it generally goes through some pre-processing to organize it into structured format. So it uses unstructured data, then we have to do pre-processing to make the data structured, so it depends on the specific algorithm that you use in machine learning itself. It depends on the specific type of algorithm that you use. So if you use a particular algorithm, then you have to pre-process the data based on the requirement of that algorithm. And in deep learning eliminates some of the data pre-processing that is typically involved with the machine learning. So that pre-processing step is some of the pre-processing. So it is not fully free from that pre-processing step. Still, you have to prepare data set based on the type of deep learning algorithm that you use. These algorithms can ingest and process unstructured data like text, images, and it automates feature extraction, removing some of the dependencies on human experts. Removing some of the dependencies on human experts. So like so in case of deep learning, like if you want to, some algorithms need like highly pre-processed data. Even in case of deep learning, we have to annotate the images, and we have to prepare the data set. It might not be just the raw image. If you're trying to use images and if you're trying to use train the model based on input images, then you may have to annotate the images, and you have to create the data sets. You may have to use other type of files also, plus with the image files. So, for example, let's say that we had a set of photos of different pets, and we wanted to categorize by cat and dog, hamster, and etc. Deep learning algorithms can determine which features, example, ears, are most important to distinguish each animal from each other. In machine learning, this hierarchy of features is established manually by human experts. So that is the difference that I'm talking about. Like in case of machine learning, the pre-processing is fully, you have to make the data fully structured, tell the algorithm to recognize certain features. But in case of deep learning, uh, we have to prepare the data. For example, if we have like 1,000 images, and 1,000 images means we have in that 1,000 images we have cats, dogs, and hamster. We cannot just leave that as input. That 1,000 images as input. We have to categorize. We have to annotate all the cat images and label them as cat, and we have to annotate all the dog images and label them as dog, and then we have to annotate all the hamster images and label them as hamster, and etc. So once you're done with that labeling, then the algorithm itself will decide what is decide different features of a particular class. So if you take cat ears are different from dog ears. So cat nose is different from dog nose, or the eyes, or the overall body structure, tail, feet. So many, there are like so many like hamster, dog. So if you compare all these things, they all have the common features, like they all have ears, they all have legs, they all have paws, or and they all have mouth, nose. So all these things are there, but the shape of each of these individual features are different for each class. Each of the animal it is different. So the deep learning algorithm will on its own, it will decide what are the common features. So based on the common features, it will decide the object that it is detected, that it has detected is a cat, dog, or a hamster. So for example, so if you think in from that point of view, we can understand that deep learning, it is just identifying patterns. So it is identifying common patterns. So if you take dog, any type of dog, yeah, it has some certain common features that sets it apart from other species, some other species, such as cat. So if you take cats, any type of cat, any type of house cats, whether it is a stray cat, or whether it's a pet, any type of specific breed of pet cat, it could be they all have common features, and the job of deep learning algorithms is to find out these common patterns, and based on the common patterns, if the common patterns fit a certain model, then it is a certain object. So that's how it is recognizing. So it is simply just doing pattern recognition in images. So that is one example of deep learning. And then, so that's it about deep learning. So we have to cover the next thing, that is robotics. So we will be using deep learning in robotics. So definition of a robot, a machine, especially one programmed by a computer capable of carrying out a complex series of actions automatically. Robots can be guided by external control devices, or control may be embedded within. Robots may be constructed to take a human form, but most of the robots are machines designed to perform tasks with no regard to how they look. So this is just a simple definition of a robot. You can just read it and understand. Yes, there is nothing much complex about this. Just simple definition of what is a robot. And then history of robotics. Like robotics already existed even from ancient times. Robotic already existed, like in Greece, Egyptian times. It already existed, but in a different way, like water power for ceremonies. Is not electricity wasn't invented, so they were able to like make the kind of robots that we were able to invent in 20th century. But still, we can say they are like different type. And in 14th century to 19th century in Europe, uh, clock driven for entertainment purposes. So we can see like different clothing movies and different type of old robotic setups with fully based on clockworks. So you can feel like different type of old stories and novels. We can say like people creating robots with the clocks, different types of clocks and gear setups, and then motor driven than actual robots. 20th century actual robots, motor-driven robots. First motor-driven robot, Automata, Unimate. So Automata was the first motor-driven robot. Then Unimate, first industrial robot. Shaky, first autonomous mobile research robot. And Stanford Arm is the first dexterous electrical motor-driven robot. So we'll see all these different robots like Unimate, designed and developed by George Devil. Unimate was the first industrial robot which worked in General Motors assembly line and in at the Inland Fisher Guide Plant in Ewing Township in New Jersey, 1961. And then Shaky Charles Rosen, designed and developed by Charles Rosen. Shaky robot was first general purpose mobile robot. So it's a general purpose mobile robot and robot to be able to reason about its own actions. So while other robots have to be instructed on each individual step of completing a large task, Shaky could analyze commands and break down them into basic chunks by itself. So in case of no other robots, specific robots, we have to give each and every command. But in case of Shaky, you can give a set of commands and it will or a single command that comprises of like small task. The shaky can separate these one big command into small tasks and it can execute these tasks. So it's a general, that's why it's called a general purpose robot. Then Stanford Arm is a Victor Chainman. Stanford Arm is an industrial robot with 6 degrees of freedom designed by Stanford University by Victor Chainman in 1969. Then, so if you take robotics development today, we can talk about robotic operating system, ROS. So our robot operating system. So robot operating system is a open source robotic middleware suite. So it is like it is not like a conventional operating system. So if you take a conventional operating system like Windows or Linux operating systems, they are fully implemented in a single hardware, in a single machine. So if you take a laptop, the system that I'm using here, I'm using a laptop, and the laptop has a Windows OS installed, and this Windows OS resides fully in my laptop. So through this OS, I can access different hardware and hardware parts of the machine, and I can use it for running different software applications. So the same with that same idea, if you explain ROS is not that type of a operating system. It resides in multiple hardware. So if we take a single robotic application, so any kind of robot, there could be multiple hardware devices. So there could be sensors, like different type of sensors, like ranging sensors, or camera. So this can only be interfaced with the computer. So we cannot use a simple type of microcontroller for interfacing high-end sensors like LiDAR sensors or radar sensors or 3D cameras. These devices cannot be interfaced with a simple microcontroller. So we need we need a single board computer or we need a normal PC for interfacing that sensor and for processing the data from that input data from that sensor. Then the motor should be controlled. So for controlling motor, we need a simple microcontroller. And then we can do the high-end processing. Maybe the single board computer that we use is not, the mini computer, that embedded computer that we use is not capable of processing that much of data with that much of speed. So that means we can use some other high-end application in our own PC. And then we can make the PC as part of the system, robot system. So in that case, we can install ROS packages in all these different systems. We can install ROS package in our PC. By just installing a Linux OS in our Ubuntu OS in our PC, we can install ROS packages in that Ubuntu OS. Then we can use libraries, microcontroller libraries, for connecting microcontroller to the ROS network. And then we can use like another Linux OS for single board computer. So all these 3 hardware systems are interconnected using a single operating system robot operating. That is called robot operating system. So all the so it is OS independent. So it is independent of different type of operating systems. So Windows OS can communicate with the Linux OS. Linux OS can communicate with the simple Arduino program. So although ROS is not an operating system, but a collection of software frameworks for robot software development, it provides services designed for heterogeneous computer clusters, such as hardware abstraction, low-level device control, implementation of commonly used functionalities, message passing between processors and packages. So message passing functionality, low-level device control, all these comes under the same things that I just explained. Like we have multiple devices, so multiple devices need to be intercommunicating. So you can use message passing for that. And in these multiple devices, we need to access the most basic type of hardware elements. Hardware elements like the GPIO of the microcontroller or the USB of the single board computer to interface the LiDAR module or camera module or a camera interface that we need to access for accessing data from a camera module, from a 2D camera module. All these are hardware elements that we need to access. So ROS has different type of packages that can be used for accessing all these hardware. So that's why it's called hardware abstraction. Hardware abstraction means the hardware can be accessed through certain set of software packages. Any hardware, so that we don't need to directly bother about or learn and bother about the hardware and its complexities. We can directly access the hardware abstraction layer. So hardware abstraction layer is just a set of softwares, software packages we can use to software packages and functions that we can use to access the hardware. Then ROS, hardware abstraction and low-level device control, created by California Willow Garage, now maintained by Open Source Robotic Foundation. Plumbing tools, capabilities, ecosystem, all this comes under ROS. So then, so just the same thing that I just explained, hardware abstraction. What is hardware abstraction? What is then ROS, like what is ROS? Plumbing tools, capabilities, ecosystem. So plumbing means message passing. It uses publish and subscribe model for message passing between different nodes. And ROS provides an extensive set of tools for configuring, starting, introspecting, debugging, visualizing, logging, testing, stopping, and distributing computing systems. So different type of tools that are available in ROS and capabilities provides a collection of libraries, implementation, useful robot functionalities with focus on mobility, manipulation, and perception. So like autonomous navigation, like object detection, or like pathfinding. All these are like different type of common functionalities that a robot need to have. So these can be implemented easily using ROS because ROS has inbuilt packages and libraries which are already implemented all these functionalities. Then in ecosystem, ROS is supported by and improved by a large community with a strong focus on integration and documentation. Then some key factors like hardware abstraction, programming language independent. So it is programming language independent. To develop a single ROS system, you may have to program multiple languages. You may have to use XML and you will be using Python, C++, C based on your application. You could use any type of it is programming language independent. Implementation of a wide range of commonly used tools and algorithms, message passing between processes. So that is OS independent and standardized packages for management, useful set of shell commands and utilities with tab completion. Then ROS concepts, ROS concepts and components, like mainly ROS client libraries available in Python, C++, Lisp, and MATLAB, experimental client libraries in Java and Lua, then supported operating systems. Mostly people use Debian-based systems, like Ubuntu systems can be used, and also we can use Debian-based systems. Mostly Ubuntu system is used when supported robots that are already implemented, different type of sensors that can be used in integrated hardware. Then there are simulators. You don't need to buy hardware and learn about ROS. You can use simulation you can use different type of simulators to learn about ROS. So like you can use, there are two type of simulators that they are commonly used. Stage and Gazebo. Stage is a 2D simulator and Gazebo is a 3D simulator. So you can make your own robotic applications using these simulators. So the software part is exactly same. Only you have to implement the hardware part. So hardware part won't be exactly same as a simulation. Simulation is much more easier than a real hardware implementation. Then about robots. So these are all general information about robots. We don't need to go through all this because these are like basic robot things. So tomorrow we will learn about in the third session tomorrow we will learn about the single board computer called Jetson Nano. So we are going to use Jetson Nano in our practical examples. So Jetson Nano is an AI board from NVIDIA. So it is used for any different type of AI developments, and it is majorly used in artificial intelligence and robotics. So it's a single board computer, it's an embedded computer. So it can be used for developing AI applications and also can be used for developing robotic applications with the AI. Because if you take this single board computer, it has all the different kind of processing capabilities as a normal PC with a GPU and CPU, and plus it has all the different capabilities of a simple microcontroller. Like it has like different peripheral interfaces like I2C interface, SK interface, UART interface, and we can use the pin headers here, like the pin headers, the expansion headers here for GPIO programming, like simple input output programming, and all those things. So today we don't have the time to go into Jetson Nano. So tomorrow we'll see Jetson Nano. I'll give you an introduction to Jetson Nano, and we'll see some applications using it. Jetson Nano, how to configure Jetson Nano. We'll see how to configure Jetson Nano, how to get started with Jetson Nano, and how to just make a simple application using artificial intelligence, care about robotic application using artificial using Jetson Nano. So today that's it for today. So we'll continue from tomorrow. Tomorrow we can clarify any kind of doubts that you have today. Today I have to wind up the session right now. We don't have time, so we have to wind up the session right now. We don't have time for Q&A. So thank you everyone. Thanks everyone for listening. So we can continue from tomorrow. We can join at the same time. 7 o'clock we'll continue the session. We'll see about Jetson tomorrow. Thanks for listening.